Okay, so, oops. All right, so good. So let's see. Fred, you can tell me if you can hear the report. All right, so good morning. Let's start our third lecture dedicated to the introduction to quantum chromodynamics and the pattern model. So, okay, so I hope you had good dreams and okay. And you were dreaming about the picture of the proton as we see inside the collider, right? So we had a little timing right before on the end of the last presentation. I asked you, well, think about the following. So if we literally assume that the colliders are like to behave like E microscopes. So the microscopes take pictures, right? Now they take pictures in the unusual way, but for example, let's say they say we take deep inelastic scattering that is shown here. And very often you will see that you will hear that deep inelastic scattering really behaves like some kind of a microscope that can, for example, do the three-dimensional picture of a proton or the nucleus, let's say the electron collider. And the way it works is the following. So, well, this is the Feynman diagram that describes the probability for scattering. But what happens in reality is that this photon that is deposited by the electron is a space-like photon. And literally what you could imagine is that we have a proton passing by and the electron somewhere, well, in the vicinity, but not exactly at the location of the proton. So the proton, the electron emits a photon, but which is space-like. It disappears at one point, it appears at the other point, which is separated by a space-like distance. So that it's basically a really quantum tunneling effect. And then if this deposited photon ends up in the place which is occupied by the proton at the time. So the photon will interact with the quark and will produce some residual effect that you can observe in the detect, right? So it is kind of works like, if you think about it, it works similar to what happens with the optical microscope where you scatter photons on an object that you see, and here, well, you kind of do the same kind of scattering, except you scatter one photon, one virtual photon at a time. But then you can ask, well, suppose now we try to reconstruct the composite feature of the proton, right? We go through this kind of multiple scatterings, and you kind of do an average, right? And so then the question here is that how does the proton look like in space and time, right? And so then, of course, you see various kinds of pictures, like including on this book, so they try to show how the protons that lights they appear in scattering. But the question that I asked you is that what if you were trying to imagine among various pictures, which picture is the most appropriate? And then let's see if we have any ideas. Like if you want to look at these various pictures, so how do you draw the proton that we see in the collider? Like if you look at these pictures, for example, are they close to the reality you will actually see in the collider or not?
And the energy of the photon, right?
Yeah, can you speak up, please?
I think it depends on the energy of the photon.
Yeah, so the photon here, you assume that the photon is it's really like the short wavelengths photon, right? So therefore, you kind of like, just like with the visible light, our wavelengths is very small compared to the size of the object, right? So that's why we have a high resolution. Well, here we have a high resolution photon, right? And so therefore, literally, they can kind of reconstruct these images pixel by pixel, if you like, right? So okay. But then how will this picture look like if you reconstruct it from this distance? So any of those three pixels pictures that appeal to you or not? Which one? The green one? Or which one? That one. Can you tell why? Yes, you have to because you
Yeah, I was thinking about why is there a lot of energy? So I had energy, but I'm studying emotion drugs, but there's so yeah, I can see clearly 3 quarks in the top.
Okay.
So that's what
Okay. Good. So that's one possibility, and that's what on the book, right? So okay, other ideas. bottom right, so okay, tell us why.
Because when you observe the nucleon, you cannot differentiate between the quarks that are coming from the valence region or the C region. So that's kind of, it improves everything. Like has all the C and it will have 3 valence quarks inside it, but you cannot pinpoint those values.
Okay. Yeah, so here okay, so what's important, of course, is that it also there is the picture will depend on the typical momentum crash, right? And so here, like, well, if like what Professor Romans will telling you yesterday, if you look at, let's see, the valence quarks in the proton, so they get the momentum crash in X about 1/3, give or take, I don't know, 10-20%. But this is the picture of the proton when it grows very small. The objects with very tiny momentum crash, right? It doesn't really look like this kind of, I don't know, ellipse. What do you think? Okay, so we observe it again. So the proton is essentially moving essentially with the speed of light with respect to us. Well, okay, so the legs contraction, actually, you never see legs contraction. And the legs contraction, that's one of these conceptions that you pick up with some special relativity course. The legs contraction is never observed. So the only thing that was the legs contraction is really, well, it's a property of the mathematical transformation. So, roughly speaking, if you measure the distances in one frame, and you compare them to the distances without the frame. So then you compare the numbers, then you have the legs contraction. But you don't see by eye. For instance, so you see something else by eye because you stay in the same frame and you look at it, so you cannot see the legs contraction. You have to be in one frame. Okay. Well, actually, this is let's think about it. So, for example, let's think. Okay, so very often you see people draw this proton as a pancake. They say protons look like a pancake when we scatter them, okay? So let's try to kind of visualize what happens. Think about the following. Can you visualize radiation from a highly boosted object? So what we said is that when you look at quarks inside the proton, they're kind of loosely bound particles. They are really like electrons. And so they need the gluon field, and the gluon field also, when you look at very high energy, low short wavelengths, gluon field is really behaves like an electromagnetic field radiation. So the question to you is that can you visualize how an electron will radiate the electromagnetic field, right? So well, so what would be the picture? For example, imagine we have an electron, well, and it radiates a wave, and let's assume the electron is depressed. So how would the wave look like when it radiates the wave? So you have an electron at rest, and it radiates the wave. What would be the shape of the wave that it radiates? Spherical, right? So spherical. So therefore, you have an electron that when it is at rest, it will be something like this. Let me see. I have it here. So okay, so this is a simulation. Basically, well, this is an electron now. Here, I assume that it's just a sinusoidal wave, a harmonic wave, but in general there will be some wave packet. But when the electron radiates something, so the wave goes in all directions. Okay, now the question to you the following. Now imagine, so this electron moves in the plus z direction. So now draw the wave fronts. How will the wave fronts look like? And so that's why I asked you to bring the paper today, draw it. So now imagine that the source moves to the right. So draw the wave fronts. So how will it look like?
Isn't it the same? Because
Well,
radiation is only with the speed of light, so it doesn't matter reference.
So yeah, so basically one idea would be that okay, you still have the spherical wave, right? So it goes in all directions. Okay. Other ideas?
What's beta?
Well, the beta here, okay, so let's assume just because it's hard to grow for very large beta, so we'll assume it's moderate, right? So that we can still grow it with small beta transfer. It's small, no. Yeah, so then we can also ask what happens when you have a large beta, right? So it's actually, okay, but let's try to grow some moderate data. Moderate speed, right? So the body over speed.
Are you gonna get wave bunching?
Huh?
Are you gonna get wave bunching?
Well, okay, so this describes any kind of function that oscillates. So expressed like a wave. It can be wave function, it can be intensity, well, not intensity, yeah, not intensity, the amplitude, right? So it's just a solution of a wave, some wave equation. Okay, so yeah, did you visualize what happens? So draw it in both in all directions, right? So try to imagine what happens. Well, here this you have spherical. Try to draw what happens in all directions. Okay? So not just the plane wave. Yeah, these have anyway. If you need this, maybe have some physics besides that should do that.
Yeah, like a boat.
Doppler, okay.
Like the waves of both peaks. But
Yeah, okay. So let's see. Okay, good. So does anyone want to show to me what you got? Okay, good. Good. Yeah, that's nice. Okay. All right. Really good. All right. So now I have a simulation. Let's compare to what the simulation tells us. So now what I will have is the following. So instead of one source, I will have three sources. And so they will all move to the right. Okay, so they will basically move from these points, 3 points to these 3 points. And they radiate. Okay, sorry. You already see the answer, but okay, so let's see the simulation. All right, let's pause here. Okay, is this what you've got? More or less? So, yeah. Yeah, very good. Perfect. Okay, so now let's see what happens. So basically what happens is basically it's what is called the Doppler effect. And so whatever radiation goes to the right, it cannot go faster than the speed of light, right? So basically whatever radiation goes to the front is compressed, right? So the wavelength is shorter when you go in the right direction. The radiation that goes backward is extended, right? So it is extended, and you have this shape where whatever was radiated to the right in the past, it's all squeezed in this region here. And now imagine the faster this object moves, the more this radiation to the right from all the history from the past, it is squeezed in this very narrow region here, right? So in the front, and everything behind is extended, right? And so then if you write the equation, what you will see that for the radiation that goes to the right, for theta equal to 0. Now, if you were okay, so again, that's if you were just having the spherical wave, so you'll have the radiation that goes like some amplitude f0 cosine k prime r prime minus omega prime t prime, and so this is all measured with respect to the source, okay, divided by r prime, which is the distance, right? And so basically that's the expression for the spherical wave. Now, in this case, the wave is isotropic, so it is spherical, right? So now, if you look at the wave of the moving source, well, now we have this distortion that you saw, right? And so then again, let me play and while I'm talking. But basically, the wave that goes exactly in the forward direction, well, it has not the previous cosine dependence, but it has dependence cosine k plus times x minus. Right, and x plus and x minus are those coordinates that I was describing to you. And the backward wave has dependence cosine k minus x plus. Okay, and all the energy of the radiation forward is now squeezed in this shock wave here. And all the energy which goes behind, there is an afterglow. Okay. So then what you also see therefore is that actually you can apply the uncertainty principle. You will see that lots of energy in the proton is deposited in the shock wave, and then there is an afterglow. Okay, so then now if you were now to visualize what happens with the proton, well, the proton is not exactly an electron, right? So the partons, they are free, quasi-free inside the volume of the proton. But now if the radiation goes outwards, well, there is a confinement effect. And so the way you can think about it is that, like, if you look at the Svelitz quartz, if you look at the simulations of inspiring gravitational waves. So basically you have quarks rotating, radiating because they have that acceleration. And so there is this inspiring gluon radiation going out. But the gluon radiation cannot go very far because you start getting a confinement effect that essentially happens because the vacuum medium response changes. So basically it's really like you have some kind of non-trivial permittivity and polarizability of the vacuum. And so then this whole proton behaves more like this spiraling sources that radiate, but in the cavity with a reflecting wall. So everything bounces back. And so this whole thing travels to the right, but then most of the energy will be sitting here on the shock wave. And so whenever the protons scatter, it's really, well, okay, if we talk about the hard scattering, it's really the effect of the scattering of the shock waves where the partons are more or less independent. But you also have the interaction with the afterglow. And there is a huge extended volume of the afterglow. So then depending on how you again, accelerated the protons, this afterglow can be more or less important compared to the shockwave scattering. Okay, all right. So then now the important thing is that again is the following: that waves that are radiated in the past in the proton's rest frame have compressed into a small interval delta x minus kind of along the shockwave here. Okay, and the future has extended in the large region with a large x plus, and that's what precisely we discussed like last in the middle of the second lecture. We discussed this, well, basically what are the typical sizes in the light cone coordinates, right? So well, here we see that most of the proton energy is squeezed in the small interval delta x minus, which according to the Heisenberg uncertainty principle corresponds to large delta E plus. And then it also has, the afterglow, which has large X plus, which is not, now you have less energy there. You have so now large uncertainty, then it has a small, so it has a large uncertainty delta P minus in that case, right? Okay, and then therefore you expect that scattering on the shock wave is more or less independent from what happens in the afterglow, basically. So you can think that you can factorize the dynamics on the shock wave from the dynamics in this radiation that is extended, and it has kind of gluons with very long wavelengths. And so that's basically these corrections that you will apply to the Parton model that you have to consider. Okay, all right. So what I described to you is basically it's a basic property of the relativistic transformation of the boost, right? And so here, by the way, I was showing the transformation on the spin zero field. I didn't tell you that the fermions have spin 1/2 or gluons have spin 1, but you could imagine that there are similar transformations that are also applied to fermions or vector fields. And basically, in that case, you transform not only essentially the coordinate x inside the field, but you also transform the components of the fields according to the rules that are given by the Lorentz transformation rules. Okay, but okay, so still you apply the same intuition about factorization. And so this intuition about factorization is basically the core of the logic about the Parton model. So Feynman, when he was thinking about high energy scattering, he didn't know what kind of particles were inside the hadrons. What he knew though is that if you accelerate the object to the speed close to the speed of light, you must have some kind of factorization that I described. So there will be lots of hard scattering from the shock wave, and there will be additional correction from the long distance scattering due to this afterglow. Okay, so that's kind of a big idea. And it applies to QCD. It also applies to any other kind of scattering of, well, let's say, objects that can be weakly interacting when they are squeezed within the short volume of space and time. Okay. All right. So that's kind of hopefully what gives you some idea about the physics intuition behind factorization. So what, again, so the big idea here is that relative speeds of hadrons are close to speed of light. Now, particle coordinates are tight dilated and Lorentz contracted along the direction of motion. So here we talk about coordinates. We can talk about Lorentz contraction, right? Now, if you get a kind of natural understanding of what happens if you use light cone coordinates, right? And so then now inside the shock waves, because of the time dilation, so you actually compared to the time it takes for the shock waves to pass through each other, so the particles don't have time to move. Basically, you can literally assume because of the time dilation, the shock wave is literally frozen. And that's why we can talk about the probability distribution. So you can say, okay, in the first approximation, particles scatter incoherently, and probability for knocking apart now the shock wave is given by the probability distribution that doesn't really care how quickly this interaction happens, right? So that's the big idea that leads to the kind of the important property of factorization and important property of pattern distribution function, right? Now, let me pause here. Do you guys have any thoughts or questions about this? Okay, so that's the intuition. Now, of course, again, so you can ask, well, yes, sorry.
So, how do we compare the time scales of interaction in a collision and interaction within the
Well, so the interaction within the nuclear, again, so you can apply the Heisenberg uncertainty principle, right? So it happens that, well, if this time interval of a lot of, I don't know, one inverse term or something like that, right? And the collision is much faster, right? And so furthermore, there is the time dilation effect. So you need to ask what frame you consider, right? So, right, but essentially, you know, for practical purposes, collision and it's different games. Right. Now, of course, what we can say, okay, this looks like it's a kind of a pretty picture, and yes, it's not the picture that you get from the media, right? So then you ask, well, how do you know that this is right? And so then for you to prove that this is correct, you need to kind of systematically think about contributions from different radiation sources and how to separate them or characterize them. And this is very non-trivial. So there is a proof of factorization that exists for a process like this, and also maybe for the brilliant process, but in general, this intuitive picture is very hard to prove mathematically because it's just so complex, and so therefore, okay, so what is the one and two proofs of factorization? But let's take a closer look at mathematics in the context of deeply inelastic scattering. Right. So, okay. So what I'll kind of go through the same ideas now, but looking at the equations, right? And so first of all, I'll quickly show you the slide. It's actually, okay. So it's not was shown this time, not by another speaker, but was shown by Dan. So basically, if we look at deep inelastic scattering, so L here stands for the electron, H stands for the proton, right? And so I mentioned to you that you can introduce two variables. Q squared determines the virtuality of the photon, or if you like, it determines the typical resolution scale wavelengths of this photon. And X determines the typical momentum fraction that is passed in the lowest order contribution when you have no additional radiation in the photonic process, right? And so then you have these two variables, Q squared and X. You mean, okay, so now deeply inelastic means that Q squared is very large. It doesn't have to be infinite, but it is much larger than 1 inverse GV squared. And now we will assume for a moment that X is fixed. So when Q squared goes up, we assume X, it doesn't, okay, so it's close, let's say, to 0.1. It doesn't change much. Okay, so then this picture that I will describe to you applies when Q squared is large, X is not too small. X does not go to zero as Q squared goes to zero. And then I'll quickly tell you what happens if X does go to 0. Okay, now then there are other variables like the inelasticity variables or the total energy of the photon-proton collision. I will not talk about those for now. Okay, but then another thing that Dan told you is that just based on this pattern model picture, in the spin structure of the interaction between the electron and protons through the photon exchange, you can decompose the cross-section for deep inelastic scattering into what I call the leptonic tensor or in the hadronic tensor, where the leptonic tensor only depends on the momenta of the electrons, and the hadronic tensor only depends on P, the momentum of the hadron, and Q, the momentum of the photon, right? And so furthermore, because of the Lorentz structure of this contraction of these tensors, we can introduce what I call structure functions, right? So we can write this hadronic tensor, which is called here W, in terms of in general, three structure functions, F1, F2, and F3, that are multiplied by some tensors describing the structure of the Lorentz group for the scattering. And so the structure functions, they only depend on X and Q squared. And so now the dependence on Q squared actually comes from the high order correction. So if you only look at the lowest order, if you only look at this picture that I described for the pattern model only. So the structure functions, they are only functions of X, the momentum fraction that is carried by the pattern. If you include high order corrections, and I'll briefly show how this emerges, the structure functions will also depend on the resolution scale, Q squared. Okay, so then was showing to you various kinds of structure functions. And so again, so for example, this is another slide showing a relationship between F1, F2, which always appear in both neutral current and charge current AS. And then what Dan was pointing out is that in fact, F2 is more or less like F1, but which describes a scattering of transverse photons on the hadron. But then in general, there is also a contribution from the longitudinal photon scattering, which is described by the structure function FL. And then F3, sorry, you cannot see it well, but F3 only appears in parity violating processes. And so therefore, for now, we will neglect it. Okay, now what's very interesting to discuss is how this scattering happens in the space-time picture, like the one I was describing. And we can do a quick analysis as follows. Let's assume we go to the brick wall frame that I introduced yesterday, and look at the momentum components of Q and P in the light cone coordinates. And now what you should realize here is the following, that, okay, so for Q, you have both the large plus component and minus component. And we can assume Q goes to infinity, it's a large scale here. For P, however, in the bright frame, if X is fixed, then the plus component is large and the minus component is small, right? So it's one is proportional to Q, the other one is inversely proportional to Q. We assume there is no transverse momentum at this order, right? And at high orders, we'll also include the effect of the transverse momentum, right? And okay. Then what, okay, I also mentioned to you the delta X plus, delta X minus, delta P plus, and delta P minus, right? So those will be also very important. In roughly speaking, I was discussing the width of the shock wave that is given by delta X minus in this case. And I was also discussing the resolution of the photon. I said that, okay, if Q is large, the photon behaves more like a pixel probe, right? So how does that work? Well, you can start, for example, this by looking at the typical size of the proton in the rest frame, where both P plus and P minus are order M. And so therefore, by the Heisenberg uncertainty principle, both delta X plus and delta X minus are of order 1 over M. And then you can do a boost from the rest frame of the proton to the brick wall frame. So the boost factor, you can prove it at home, goes like Q over M times X. M is the mass of the proton, right? So therefore, in the brick wall frame, delta X plus will be scaling like Q over M squared over X. Delta X minus will be scaling like X over Q. So delta X minus is small. the size of the shock wave is small. Delta X plus, the size of the afterglow is large. Okay. All right. So then now, but the virtual photon, okay, we will look at just in the collision frame. Well, the size of the virtual photon is simply determined by Q, capital Q. It's virtuality. So therefore, the size for the virtual photon is simply delta X plus, which is a order 1 over Q, right? And so now what you see therefore is that when you look at the afterglow, in the proton, it has a much larger size, delta X plus, which scales like QM squared over X. And the proton, however, knocks out a much smaller piece of the proton, right? So therefore, so with this kind of setup, really whenever the photon hits the shock wave, it knocks out the partons that are essentially free because the size of the typical parton is very small. It's of order 1 over Q in this case. Okay. Now, however, so therefore, in the first approximation, you can say, okay, so whenever we see, let's say, the bright picture of the proton, well, it happens because the photons interact with these very tiny partons in the shock wave, and that's the only possibility. But that's not entirely the case because sometimes you also can have partons radiating with this afterglow. And therefore, if you would like to evaluate high order contributions, well, you need to include long distance effects. And so in this, okay, here I'm showing the space-time picture in the light cone coordinates where the proton moves along the X plus direction, photon goes in the minus X3 direction, right? And so photon basically knocks out a parton at the times X equal to 0, and so the parton goes in the X minus direction because it goes backwards in the direction of the photon, right? Okay, so now if this were a parton model, so that's all that happens at the leading order. But however, there is an afterglow effect, and you say now if I would like to calculate the correction explicitly, I must also include effects of these long distance fields. And so that's what is indicated here by the gluon line. So in general, when you do the full calculation, you also include effects of this, gluon ambient field around it, right? So, okay. So then based on that, you already see that you kind of start getting this factorized picture. So then, for example, if we talk about the dominant contribution to scattering in the parton model, you will say the cross-section should go roughly like this. So you should have the hard scattering cross-section for the photon on this point-like parton, multiplied by the probability for knocking out parton. So parton here is A, out of the hadron H. You must integrate over the momentum fractions of the parton that are possible in the scattering. In scattering, it's called C, right? And so, okay, so then F of H, C mu times dC is really the probability to find a parton with this flavor A, which can be the gluon, it can be U bar D, etc. In hadron H, carrying a momentum fraction of the carrying the fraction of the plus component, the large component of the proton's momentum. Okay, and C is equal therefore to the plus component of the hadron of the parton should be A here, P plus A divided by P plus. Okay, all right. Now, this is not the whole story because first of all, so this picture will depend on the resolution scale, which is mu. But now in this process, mu is equal to Q because Q is the hard scale. We set mu, which is an arbitrary scale, factorization scale. We set it equal to Q. And second, you may have high order corrections. And you may also have this additional effects from the interaction with the afterglow, which give you corrections of order M over Q, and those are called power suppressed corrections or high twist corrections in this case. Okay. Okay, so now of course, if you don't have any radiation, so this picture further simplifies because, well, here I showed the integration over C. But if you look at work just at the leading order, well, we have the exact momentum conservation where the momentum of the incoming parton plus the momentum of the photon must add up to 0, right? And so therefore C must be equal to X. So you can just solve this equation. So there is just a requirement that the momentum fraction is equal to, yeah.
So if we're taking the momentum fraction to be X, I thought we had restricted X to be only down to a certain size in order to do this factorization so that everything was sitting in the shock wave, right? Well,
No. Here the momentum fraction. Okay, so you assume that the shock wave always commutes with the proton, right? And you just say these partons will carry essentially, well, just some fraction of the total momentum, which is from some very small value of X, which you can say is 0 in the first approximation to 1. Right. So that's kind of the picture. Yeah. Yeah. And of course, okay, so it will not be exactly 0. It will be some small value, but yes.
Here we have to sum over A, right?
Yeah. Yeah, sorry, I think I need to correct the slide. So I need to include the sum over A. I need to replace I by A here.
And then do infrared divergences that get cancelled when inclusive appear at the leading order level or at the M over Q level?
Well, so M over Q, yeah, actually they will have the soft divergences, but I will not get there. Now in this leading power piece, the soft divergences only appear at the NLO in the higher. There is no soft divergence at the leading order, because to have a soft divergence you need to radiate something. Here you don't have radiation yet.
And that kind of radiation will happen at the order M over Q or just at the next level?
So the radiation will happen both here, and it will also happen in terms of order M over Q. And of course, it's much more complicated in terms of order M over Q. In fact, I don't know if people can calculate it there. So yeah. Other questions? Okay. Okay. So now, all right. So then also here I wrote the expression for the cross section. All right. But also I would like to point out, of course, that the cross section is constructed from the structure functions. So therefore, the factorization also holds for the structure functions. And here I wrote an expression, for example, for the structure function F2, right? So if we work at the leading order, so C is equal to X. So therefore, the F2 will be equal to well, you can convince yourself very easily. It's an easy calculation. So then, well, all the prefactors in this case are very simple. And F2 is simply equal to the sum of X times Fi of H, where I only runs over quarks and anti-quarks, times the fractional charge of the quark squared. And so this is the leading order term. Now, we neglected corrections from radiation of the gluon. And so the first correction will come at order alpha S, right? So if we can calculate that, right? And then we also neglected corrections of order M over Q. Okay, so therefore you need to keep in mind whenever you see that this factorized formula, well, there are corrections. You don't just, okay, so sometimes they are not important, but in many cases, for example, the N-log correction and nowadays even N3 log correction is important. So therefore now if you include N3 log correction, well, we can no longer assume that C is equal to X. We need to integrate C from 0 to 1 according to some prescriptions that introduced by the momentum conservation. And in that case, the missing correction is of order 1 higher in alpha S. So if you calculate it in terms of order alpha S to the power P, so the missing correction is alpha S P plus 1. And again, you have the power suppressed terms. Okay, so you have to keep in mind that always there are these corrections, and if you let's see the calculation for Jefferson lab, so these both kinds of corrections will be important. Okay, all right. So then now let's talk a little bit about the hard scattering cross section. So for the hard scattering cross section can be actually calculated to essentially arbitrary order, at least in DAS. Except, of course, every high order becomes more and more complicated. And the idea here, you start writing additional diagrams, right? Like, for example, at the leading order, you had a quark coming in, scattering on the photon. At the next to leading order, this quark can radiate an additional gluon, or you can also have the gluon coming in, splitting in the QQ bar pair. and the photon scatters on one of these quarks. And so basically you need to write all these diagrams, and eventually all flavors, including the gluons, will contribute to the scattering. Okay, now something that again I will quickly flash that I have a couple of slides to kind of again summarize results from the pattern model. Like for example, that F1, F2 is equal to 2 times X times F1. You can take a look at it. And yeah, so then I guess, well, essentially I have a few slides kind of repeat what Dan was already saying. And as I have said about the structure functions, and we can come back to them during the recitation. Okay, now what I would like to do is spend another couple of minutes talking about space-time picture. And so far, we talked about the space-time picture for a very highly boosted proton, where the proton, essentially kind of flashes by next to us with the speed of light. And then what we found is that now the scattering in this case appears more or less like the proton was traveling and suddenly hit this little pixel where the photon sits with a high energy, and the pixel knocked out something out of the proton, right? So the pattern. So that's one picture in our lab frame. Well, you could ask, what happens in the rest frame of the proton? Well, that's an interesting exercise. Now, in the rest frame of the proton, however, of course, the proton is at rest. So the proton is spherical. It's kind of, doesn't move anywhere. So then a very interesting exercise you can do is to ask, how do you understand deep inelastic scattering in the rest frame of the proton? And sometimes it's very useful. Well, in the rest frame of the proton, so you have a kind of switched order of the events. So in the rest frame of the proton, what happens is that long time in the past, so the photon split into the QQ bar pair. And so the photon fluctuated into what is called a color dipole. And so this dipole travels through the medium of the proton. And so the dipole interacts. Okay, so then eventually after a long time, the proton falls apart because the photon created a major damage to the structure of the proton, right? So that's how it looks like, right? Okay, so that just to again summarize how this happens. If we were in the brick wall frame, right? So then the typical sizes of the proton are given by this, right? So the plus size is large, minus size is small, and the transverse size is also small, but the transverse size is large. It's about 1/m. But the sizes of interaction points are like 1/q, 1/q, and infinite in the transverse direction. Okay, right? Okay. Now, an interesting question is the following. So imagine now. Okay, so I was telling you that this is easy to understand when x is large. What happens when x is small? Right, so like for example, at LHC, we will have situations when x is small, like people now talk about large hadron electron collider or muon ion collider, where typical x will be small. Well, the picture that I described, which is called the Dikla picture, will not exactly work there. Well, and why is that? Well, because now look what happens. So let's first look at the boost factor. So the boost factor, I was showing to you, it is equal to Q divided by n times x. So you have a small x, so the boost factor becomes tremendous. So it is enhanced both by Q and 1/x. Okay, so then you have this photon coming in, but now because so first of all, the shock wave becomes extremely thin. And so it's very unlikely that the photon will hit the shock wave. It's much more likely it will hit the full afterglow region. Okay, so therefore there will be less interaction with through the traditional parton channels and more interaction with this afterglow. But also because now everything is so dilated, there is lots of time for the photon to radiate additional radiation in the rest frame of the proton. So therefore, really the interaction is not so much between the structure of the proton and the photon, but it's the interaction between the dipole and the afterglow radiation in the back of the proton. So therefore, the dynamics now at small x becomes very different. And that's why, again, when we talked about how the pictures of the proton, so the picture of the proton at very small momentum fraction will be more determined by this kind of interaction. So you will never see any effect of the valence quark. It will be just sort of well, some kind of fuzzy picture due to this scattering on this extended radiation. Okay, questions? Okay, so then now let's talk a little bit more about this pattern distribution functions. And so something that I already mentioned is that the pattern distributions depend on the resolution scale, right? So the size of the photon probe, which goes like 1/q, right? So therefore, okay, so now in the first approximation, this resolution scale mu, well, is Avogadro Q, and we have a special name for it when the scale appears inside the pattern distribution. It's called the factorization scale. Okay, so therefore the factorization scale determines the size of the pattern that is knocked out, right? And if we include the effects of the radiation, so this factorization scale, well, it's okay. So first of all, X is no longer fixed, but the factorization scale can also vary in some range, right? And how do we see that? Well, for example, when we calculate the cross sections, we integrate of the momentum over the momentum of the final state gluon, and so basically it will smear the simple pattern model picture where the X is fixed, C is fixed, and Q is there is no dependence on Q. Now we start integrating over different sizes of the patterns in the full range between 1/q and q over xm squared, right? And so therefore our full formula must account for this integration. So in fact, what you will also see is that the following, that whenever we integrate over C, right? So the range which is covered by integration is very large, because 1/q is a very small number. Q over xm squared is a very large number. So whenever we calculate the contribution to the scattering, we have to integrate over a large range. Whenever we integrate over a large range, so we typically will pick up a log of the ratio of the scale at the higher end of the integration to the scale at the low end of integration. So therefore, what also happens, and that's again, so I can kind of quickly emphasize, is that there is another way to think about this factorization, that we can have a short wavelength radiation, which is associated with the hard scattering, and the long distance radiation, which is associated with the non-perturbative scattering. And of course, if we try to calculate all radiation at once, we will be impeded by these large logs coming from the integration. So therefore, whenever we do the integral over, let's say, the virtuality of the emitted gluon, what we need to do, we need to separate contributions from gluons with very high virtuality. So virtuality is Avogadro Q, from the radiation of the gluons which have very low virtuality. And so the gluons that have very low virtuality can be assumed to be a part of the incoming proton. And so then we need to introduce a separation in scales, whereby every contribution from the radiation from the scale very large, from very small distance or very large scale Q up to a very short, longer distance, but still not too long distance, which is Avogadro mu f. So this part goes into the perturbative calculation. It goes in the hard cross section. And the rest of the radiation, well, is naturally assigned to the probability for finding the quark or the gluon inside the proton. So basically, we introduce a separation scale mu f that puts the part associated with the low virtuality or long wavelength radiation into the pattern distribution function. Okay, so then again, that's something that was already pointed out. So essentially, therefore, what happens whenever we write this factorized formula? So we have a short distance contribution that depends on mu f, and the long distance contribution of the pattern distribution function that depends on mu f. So this separation is kind of arbitrary. We really decided where we do the separation. And so therefore, in principle, the left-hand side should not depend on mu f. So in fact, if you were to evaluate the contributions from all orders of radiation, so you will get an exact cancellation of the dependence on mu f. But if you work at a fixed order, so dependence on mu f in f and sigma hat cancels up to one higher order in alpha S, because there will be mismatch in estimation of these terms between the PDF and in the hard cross sections, right? Now, this is what is called the factorization scale. It separates radiative contributions from the real gluons. Now, of course, alpha S also depends on another scale called renormalization scale. So alpha S basically, okay, so the mu or mu r in alpha S, okay, it comes from contributions from the virtual corrections, and mu f in PDF comes from real emission corrections, okay? Right, but basically, whenever we do a calculation, we need to account both for the virtual corrections and the real emission corrections. So corrections, therefore, the hard cross section will depend both on the renormalization scale and factorization scale. You can assume them to be the same. Sometimes you assume them to be different, okay? But again, so in general, there is a distinction between the renormalization scale and factorization scale. Okay. So I think I have about 5 minutes before the break, and very quickly, let me tell you that in fact this, well, okay, so the other question you can ask, well, how do I know how to construct the pattern distribution function? Well, so I already alluded to you, for example, that the factorization scale is kind of your choice, right? So you can decide how to choose it. What about the pattern distribution functions? Well, at the lowest order, you say the pattern distribution function coincides with the probability for finding patterns inside the proton. Now, if we start discussing these high order corrections, well, do we still have the unique definition? Well, the answer is that in general, no. So in fact, you can define the pattern distribution functions in many ways. In practice, there is a standard definition in the so-called MS bar scheme based on the matrix element of a certain operator, which is shown here. And again, we can discuss what this operator is, but basically, it's a kind of a generalization of the operator for the finding the quark. This is for the quark. So this is the generalization of the operator for finding the quark density, the average value for a state associated with the initial state proton, right? So this is the definition. And now, if you write the formula explicitly, you will see that this is a certain integral that involves a Fourier transform of a certain kind, right? Now, there is another, okay, so there is another interesting piece, which is called F, and the slang for it is called the Wilson line. So the Wilson line it turns out you need to put it in. So the Wilson line describes this effect of the pattern interacting with the medium gluon field. And again, you have to remember there is always the medium gluon field around the quarks, right? So now, well, from the physics picture, there must be some interaction with the gluon fields around the quarks, but also from the viewpoint of gauge invariance, it turns out you need to include a piece that describes the effect of the medium fields on the phase of the quark fields. And so this term F is precisely the term that captures the dominant effect of the interaction of the quarks with the medium gluon, long wavelength gluon fields around it. Okay? Okay, so, all right, so then something that was also mentioned, that if you now think about invariance of the total cross-section with respect to μf, so you have to introduce an equation that is similar to the renormalization group equation for alpha S, but it describes dependence of F on μf and not of alpha S on μr. And so in fact, there is not just one equation, there are sort of doctrines of the doctrines of Greek of the Parisi or Greek of Hipatov equations that describe dependence of PDFs on μf. So then the way these equations work, so basically you can calculate the derivative of F with respect to the log of the factorization scale. And this derivative is equal to the sum of pattern distributions of the scale μf multiplied by certain kernels, which are called splitting kernels. which describe probabilities for, let's say, the pattern of type B to on the right-hand side to scatter into the to scatter into pattern of type A on the left-hand side. And so the splitting kernel is called PAB. So again, they describe transition from pattern B to pattern A. So because they are short distance functions, they can be calculated perturbatively order by order. And by now they have been calculated essentially to the nth law accuracy. Yes.
This equation should equal to 0, right?
No, it's just like the renormalization group equation. So the log dependence of F. So the mu of dependence of this should be equal to 0 on the left-hand side. So therefore, the mu of dependence of F must cancel with the mu of dependence of d sigma hat up to one higher order. And so then the mu of dependence of d sigma hat gives us those splitting kernel functions.
Splitting function comes from these.
Yeah, right. Okay. All right. So then, essentially, what this Diglap equation does, it's kind of does the same sort of functionality as the renormalization group equation for alpha S. So whenever you vary math, you essentially vary the resolution scale of the PDFs. And whenever you increase the resolution scale, you can start resolving additional patterns of smaller size in the pattern of a bigger size that was observed with a low resolution scale. Okay, so that's kind of the big picture again. So in the first approximation, the Diglap equation describes the effect of this quantum microscope when you try to zoom in on the pattern distribution inside the proton. Okay, so then now, in fact, that kind of brings us to another important point, is that the properties of vectorization, in fact, they are very reminiscent of the properties of renormalization for alpha S or masses. And so just again to emphasize, we talked about the separation of scales. Whenever we talk about renormalization of alpha S, essentially we redefine the alpha S that starts to depend on mu on the scale in order to absorb or hide the summary effect of any dynamics at scales much smaller than the typical range of scales in our scattering process. So that's the effect of renormalization, right? So that goes, therefore, the only particles that contribute to renormalization are appearing in these virtual loops in this case, right? Now, if we now look at the other end, that's where the factorization comes in, okay? And so basically the factorization, what it does, if you have an observable that is not infrared safe, and something that again I emphasize that for some observables, you actually don't need to do factorization because factorization and the effect of factorization is kind of trivial. That doesn't need, it is not needed. But for observables like, for example, the cross section for deep inelastic scattering, you must factorize effects of radiation with the wavelengths much larger than the scale of our scattering of the photon on the patterns. So you must factorize it into the pattern distribution function. But however, the techniques that you use for that are very similar to renormalization techniques. And so here is a table, and again, we can discuss it at the recitation that kind of draws the analogy between various terminology and methods that we use for renormalization and the methods that we use for collinear or soft factorization. Okay, so we can discuss it during the recitation. Okay, so then now, so the other important question is how we find these pattern distribution functions. And the way we do it is the following, that we either find pattern distributions by fitting several very precise experimental measurements. We cannot calculate them yet, but we also try to calculate them on the lattice. And so the next lecture actually will discuss our techniques for finding the pattern distribution functions, right? So lattice QCD really makes substantial progress, right? So we don't need to look to kind of have a parameterization that is given for arbitrary mu. what happens is that if you just, based on what I just told you, is that if we know PDFs at some low scale mu naught, so then we can predict the PDFs at a higher scale mu very precisely using the evolution equations, right? So therefore, what we really need to do is that we need to come up with a parameterization of PDFs at some low scale mu naught of order 1 GeV. And then we can predict the PDFs and the cross sections based on the PDFs at any arbitrary scale mu using the Diglap evolution equations. Okay, and so then we need somehow to figure out parameterizations of the PDFs at a low scale to basically make predictions for PDFs at all higher scales. And so that kind of brings us to this big idea of the global fits of PDFs. Again, it will be covered in the next lecture, which is a very fascinating and very complex subject. And so just to summarize, to calculate factorizable processes, we need to know particle distribution functions, which are not arbitrary, they have a definition. So the common definition is so-called MS-Barsky definition that I showed to you, right? So the ABE is a relatively simple system of evolution equations, right? So they describe the effect of changes in the PDFs when we change the resolution of 1/q distance, right? And so then typically we will use these particle distribution functions in short distance inclusive processes where we knock out only one or a few particles plus everything else. And typically, well, at the colliders, we will have one or two initial state hadrons, right? So we feed them to experimental results or we find them from lattice QCT. Another thing that I have not mentioned is that we have similar functions for fragmentation functions. These are for the particles in the final state. And you have to apply some of the same ideas to factorization of fragmentation functions from the hard scattering cross section. Okay, and so I think with this, I think we are kind of ready to take a break. And do we have maybe one or two additional questions or comments? Yes.
Oh, I came across the most horrible way to prescribe a renormalization scheme, which is like the on-shell renormalization scheme that people use that turns off the quantum corrections just when at threshold.
Right.
Can we do this, or is there an extension of this on-shell renormalization scheme for pattern distribution factor?
Yes, you're kind of foreseeing what we are going to discuss in the next lecture. Yes, I will discuss this relation between the renormalization and factorization in the MS-bar scheme versus the on-shell scheme. And so the answer is yes. Then depending on the mass of the particle, we will use either the on-shell scheme or the MS-bar scheme. Then
we've been talking about what's called longitudinal quantum distribution function, where the function is basically a function of x, the momentum in the forward direction, the momentum. There are also theories called TMDs, transverse momentum distribution, that have been developed, and they give information about momentum distributions in the transverse direction, which we've neglected in the infinite momentum frame. And they can be determined by such things as semi-inclusive deep inelastic scattering. And that leads to something called nucleon homography.
yes.
They do these experiments at Jefferson Lab, for example. They don't do so much TMDs. Okay, but anyway, what's your opinion of these other kinds of quantum distribution functions which bring in the transverse direction?
Yeah. This lecture described a simplest type of factorization called collinear factorization. But if you have more complex observables, and one of them will be an observable that depends spontaneously on Q and QT. Well, then you find that in some regions, to properly capture this effect of all-order radiation, you need to use a different kind of factorization. And so one kind of factorization is based on these transverse momentum dependent PDFs. So then there is a relation between collinear factorization and TMD factorization. So in fact, what happens is that you will use one kind of factorization in one region for one observable and match it to the prediction based on that type of factorization with the other observable. Those types of factorization are much more complex because now you account also for QT dependence. And then this whole matching calculation is also very interesting. Now they are being developed and okay, so in some cases this TMD factorization is extremely important. For instance, if you try to measure W boson mass at the LHC, and then of course, it's still not understood very well. So you really need to, for example, the very interesting question, like what Dan has said, is that how is this picture of scattering of highly boosted objects, how does it match on this low energy dynamics that will be relevant, for example, for fixed target experiments? And so there is this very interesting transition region where, well, the proton is never at rest, but it can be relatively slowly boosted and highly boosted. And so then you see different images of the proton in these different ranges. And so then you try to eventually come up with some kind of three-dimensional tomography for different resolution scales. It's like multi-messenger, I don't know, particle physics. And so then you will have, so hopefully in 10 or 15 years, you will use these processes like semi-inclusive DS, or also another interesting question, how does it depend on the spin of the protons, or how it changes for the heavy nuclei, or what is the structure of the mesons, right? So which presumably are similar systems. So there is this whole very fascinating set of questions that can be answered using these advanced experiments with hadrons that are planned and hopefully will happen. Hopefully they will be funded and they can tell us a lot about this very interesting dynamics in a variety of energy ranges. Okay. All right. So then, Fred, when do we meet? 10:30?
Let's take half an hour.
Okay.
And 40.
Yeah. So then we have coffee the same.